The key with assigning oxidation numbers is that essentially you are treating all compounds, whether they are ionic or molecular, as if they were ionic compounds. So it's pretty easy for things that are normally ionic compounds because the oxidation number is just going to be the charge on the cation or the charge on the anion. So anything that has a predictable charge based on its position in the periodic table, it's just going to be that. If your metal is like a transition metal or one of the F-block metals that you guys haven't met very often, you're going to work out the charge by knowing what else it's bonded to. So for example, if it was Fe2O3, you see that iron's a transition metal, but you know that the oxygen is going to be the oxide ion, O2 minus. So 3 times O2 minus gives you -6. There's 2 ions. It's got to counterbalance that -6, so it's going to be iron 3. So iron will be 3 plus, the oxide is always 2 minus. So when it comes to these molecular bonded compounds, a few simple rules, okay? That oxygen is always going to be 2 minus, unless it's the peroxide ion, which you don't really come across very often. But if it is peroxide, that literally means that there is a charge per oxide. So like it's 1 minus per, so peroxide, which is O subscript 2. That is not how you spell peroxide, although it looks kind of cool. O2, 2 minus. So it's a 1 minus per oxygen, but you're probably not going to come across that, just being honest. Oxygen's always going to be -2. H will be H plus if bonded to a non-metal. An H minus for a hydride if bonded to a metal. Our lovely halogens, fluorine, chlorine, bromine, iodine, are usually going to be -1 unless bonded to oxygen. If you got halogens bonded to oxygen, like say perchloric acid or something, you would treat the halogen like it's a transition metal or something and leave the charge assignment for that halogen until last, because in a battle with oxygen, oxygen's always going to win in terms of the oxidation number. All right, so we're asked for the oxidation state of the highlighted atom. So oxygen's always going to be -2. Copper is a transition metal, so it could be anything. So let's let the charge on the copper be X. So 2 times X, then -2 for the charge on the oxygen has to equal 0. Therefore, X has to be +1. Okay, so it's going to be copper 1 oxide. So the oxidation state, we put the charge first for an oxidation state. I know. So for a charge on ion, like if it's the superscript, you put the number, then the charge. I don't know why. That's just the rule that I'm imparting to you. I don't make the rules. If you're reporting the oxidation state, you would put the charge before the number. So if you're giving the oxidation state of strontium, we know that the cation is strontium superscript 2 plus, but the oxidation number or the oxidation state would be reported as +2. Ooh, one more thing I forgot to mention. If we have an element, and that includes elements that are naturally found as molecules, I can't even type, I'm so excited. So molecular elements like O2 or P4, there's no charge associated with an element. It's going to be neutral, always 0 for the oxidation number of an element if it's just on its onesies, okay? Even if it's bonded to itself, I still count that as being on its onesies. Okay, so O2, the oxidation number is 0. Okay, H plus is a cation, it's +1. NH4 plus, we're going to have to work it out. So hydrogen, if it's bonded to nitrogen, is going to act like the metal, okay? Because hydrogen, if it has to, it's going to form like a cation. So when it's bonded to another non-metal, it's going to be the cation in this situation. So let's do a bit of algebra. Let X equal the charge on the nitrogen. And then we've got 4 times +1 for the hydrogen. And that has to sum to, it would be 0 if it was a neutral compound, but in this case we've got a cation. It's got to sum to the charge on the cation or the anion if we're doing it with a polyatomic anion. So this has to sum to +1. So X plus 4, sorry, had a bit of a moment there, equals +1. Therefore, X has to equal -3. I'm just trying to work that out in my head now and failing miserably. Let's just do it in full, right? So 1 minus 4, because that was painful enough for me in my head. So if you're following along. Let's try and be reasonable. So X equals -3. So the oxidation number on the ammonia is -3. You can always go back and check, right? -3 plus 4 will give you a net charge of +1, which is what we're expecting for this cation. Okay, should we look at some more then? I guess so. All right, so erasey time. Right, so H2, well, that's just going to be 0 because H2 is an element. CuCl, okay, so let the Cu be X and Cl is -1, and that's got to sum to 0 because it's a neutrally charged compound, so X has to be +1. So copper is +1 charge. NH4 plus, we just did that, so that was +3 for the nitrogen. Sorry, -3 even. And note how the nitride anion is usually a -3 anion, right? It's one of the predictable charges. So again, that kind of tracks with stuff that we already know. So once you kind of get the hang of this, you'll be able to do it quite quickly, and you'll notice if something seems wrong. All right, so the hydroxide ion, hydrogen is bonded to a non-metal, so it's going to act like a metal. It's going to form a cation. So oxygen is always going to be -2 unless it's the peroxide ion. So let's just check. If oxygen's -2 and hydrogen's +1, we should get a net charge of -1. -2 plus 1 is -1. So that works out. So the oxide is going to be -2. All right, one more for luck. All right, so N2, again, it's an element, so that is 0. Oh, we got something nice and covalently bonded here, typical molecular compound, so that's going to be fun. So we've got hydrogen. Hydrogen's usually going to be +1, okay? So let's let X equals our carbon, let +1 be our hydrogen, and we got 3 chlorines, and I'm going to assume that the chlorine is -1 because it usually is, unless it's bonded to oxygen, and sometimes they'll go funny, and that's got to equal 0 because our charge has to be neutral overall. So X +1 -3 has to equal 0. Let's get those numbers to one side. So X equals -1 plus 3, X equals 2. Okay, so the carbon has an oxidation state of +2. That makes sense. +2 plus 3 -1 -2 -3 be neutral. Okay, K plus is just going to be the charge on the ion, +1. H3O plus, oxygen is usually -2. Hydrogen, if it's bonded to a non-metal, should be +1. So let's just check. 3 times +1 from the hydrogen, -2 from the oxygen should equal +1. So what have we got? +3 -2, yeah, equals +1. So the oxygen is a -2 oxidation state. All right, so that is key, because if you can assign oxidation numbers to everything in the chemical equation, you can work out if it's a redox reaction or not. Remember, oxidation is an increase in oxidation number from the reactant to the product side, and reduction is a decrease in the oxidation number from the reactant to the product side. We'll come back to that in a minute.